NMR chemical shift. Have you got it? This short video quiz assesses your ability to identify a small set of regions of a proton NMR spectrum as likely evidence of a few common functional groups, including carboxylic acids and aldehydes, aromatic rings, double bonds, hydroxyl or alkoxy groups, amines, ketones, and alkyl groups. And given two possible structures and based on chemical shift considerations only, your ability to construct an argument for which structure is more likely the one corresponding to a given NMR spectrum. This quiz consists of 3 questions. It's meant to be taken after you have studied the material and think you understand it. During the presentation, you'll be asked to pause the video to at least try to solve the problem yourself and only then to continue. It won't be hardly as effective if you jump to the solution immediately. Okay, number 1. Match the 3 compounds on the left to the 3 NMR spectra on the right based on chemical shift arguments only. Pause the video while you answer this question. Okay, here we go. As always, when we're solving these problems, what we're going to do is determine the symmetry of the system, how many different groups of hydrogens we have. And we look at these spectra, we very quickly can see, here we have 3 at this one, here we also have 3 at this one, and the top one has 4 different groups. So that's significant, and we should be able to nail one of these just with that info. So let's look at the top one. We have a CH3, a CH2 next to a carbonyl group, CH3 on oxygen, 3 different kinds of groups. The next one, we have a CH3, a CH2 next to it, a CH2 next to the carbonyl, and we have an H. That's 4. And this one has an H, another H here, and the 2 CH3 groups, so that's 3. So there you go. Without doing anything else, we know that this carboxylic acid is this top one. And we can confirm that because there's nothing else that shows up around this region of 12 other than a carboxylic acid. And look, it also has 3 other different groups. 1, 2, 3. This is our CH3. This is a CH2. Here's another CH2, getting closer and closer and closer to the carbonyl group, getting pushed down until when it's next to the carbonyl group, we're in this region of a CH2 next to a carbonyl group. How about that? Okay, what about these other 2? What's the big difference? Well, on the spectrum, this is huge. This peak over here at 8. There's absolutely nothing that this could be other than this H that's on the carbonyl group of our aldehyde. That's where those come. So this is huge, and it completely nails it, and it solves the problem. There, we're done. Now, if we want to take the opportunity here to learn a little bit more, let's just check these spectra and see what we find. Okay, in the top case, we have 3 hydrogens. Well, which are they? You have this CH3 out here, which is in the alkane region because it's just attached to another CH2. So that's our CH3. And then right around 2, next to the carbonyl group, right? We have a CH2. And then why is this other peak way over here between 3 and 4? It's because it's on an oxygen. It's this guy. And what about this one down here? Well, we said that this H was delta 8, roughly, 8.1 maybe. What else have we got? Well, we've got an H way down here at 5, which is pretty unusual. But look, it's this one right here. You know, it's on an oxygen. It's not really between 3 and 4, is it? It's way down here at 5. But why? Because A, it's a CH instead of a CH3, and B, because it's not just any old oxygen, it's an oxygen with a carbonyl group. So those 2 together conspire and push this from our normal place of OCH3 to OCH with the carbonyl attached. And then we have the 2 CH3 groups. That's this grouping right here. 6 hydrogens, 2 CH3s. All right, here we go. Number 2, ready? In each case, suggest reasons why one of the two highlighted cases is further downfield, more de-shielded than the other. That is, why the proton with the higher chemical shift is more exposed and less protected from the magnetic field by electron density. Use the same inductive and resonance reasoning as we used for pKa. Now, there's a lot here, a lot of different relationships. Just come up with as many as you can and come back to the video. Okay, here we go. This first one. Well, look, we got CH3. It's in the alkane region. There's nothing special about this at all. Next to that, we have one that's a CH2 that's to the left of 2. Well, that's because that CH2 is next to this carbonyl group. The carbonyl group is sucking electrons away from that carbon, de-shielding that CH2. And then finally, we have this CH3 at 3.7. That's because it's attached to the oxygen. The oxygen is inductively pulling electrons away from the CH3. And besides that, it's got this extra carbonyl group that it's pulling electrons very strongly away from that CH3. Okay, how about the second one? Well, here again, CH3, 0.9, standard alkane. And next to it, a CH2, not on an O, just attached to another CH2. All of these are just standard alkane. And we usually see the CH2 a little bit to the left of the CH3, and that's what we're seeing here. Okay, and then we have this oxygen, which has a CH2 attached and a CH3 attached. And so in this case, what we've got is two groups in the 3 to 4 range because of the oxygen withdrawing electrons, pulling electrons away, exposing those hydrogens to the magnetic field. And then we also want to do a quick comparison between these two structures. And what we see here is the difference between an oxygen that's just an ether and an oxygen of an ester, with the ester being pulled down field just a little bit more, de-shielded because of this extra pull of the second oxygen. All right, now what about these two on the right? Well, these are aromatic systems, and they're very dramatically different. It has to do with the oxygen being able to donate a pair of its electrons to the ring, dumping electron density into the ring, and shielding whatever hydrogens are there. So that's why all of our hydrogens are at shielded positions relative to benzene, which is just a 6-membered ring, 3 double bonds, and all hydrogens. Nothing on it. Got 7.3. They're all shielded by the OCH. And notice that they're not the same position. That's because 2 of them are especially shielded, aren't they? They're to the right of 7. This is very unusual for a benzene ring. Well, if you write the resonance contributor, you see that the electron density has been placed right on the carbon that is where the hydrogen is shielded at, because that carbon is donating more electrons to the hydrogen, shielding it from the magnetic field. And we have another resonance contributor that would bring us to this other position as well. And so both of these are partially negative, and that's the shielding business. Okay, the last one. It's exactly the opposite. We have a carbonyl group. It's de-shielding. Look, 8.1, 7.4, 7.6, they're all on the other side of 7.3. They're de-shielded. With 2 of them, this one and this one, this carbon, being especially de-shielding. Why? Same reason. Consider the resonance contributors. You see that? In both cases, our plus sign, now these are partially positive at these same 2 carbons. And that partial positive charge is really pushing these electrons down further on the NMR spectrum, de-shielding them all the way to 8.1 and 7.6. Very, very dramatic. And I just want to point out that the group, this hydrogen next to these 2 groups, is at a tremendously different chemical shift, 6.8, 8.1. These are highly indicative of the sort of groups that are around the benzene ring. When we have a donating group, OCH3, we're liable to see hydrogens that are to the right of 7. And when we're deshielding with something like a carbonyl group on the ring, we could easily see aromatic protons way down at 8.1. And that is really very unusual. So it's something to think about and something to put in your back pocket as something you can use quickly to make a judgment. Okay, here's a challenge. Based on symmetry and resonance effects, match the 3 aromatic isomers to their proper spectrum. Only the 6 to 8 ppm region is shown in each case involving the 4 H atoms attached to the benzene ring. Hint, the oxygen donates electron density to the ring via resonance. This will cause H atoms at which carbons to be especially shielded? Go. Pause the video and come back when you're ready. Okay, here we go. Again, we think about symmetry. What have we got? Well, in the first case, we have 4 different hydrogens. One's near the CH3, a little further than CH3, across from the CH3, on this side near the OCH3. They're all different. How about this next one? Well, same thing, right? There's one between them, one here, one here, one here. 4 different protons, 4 different signals. But this one on the right is kind of interesting because there's a plane of symmetry and it only has 2 groups of hydrogens. So, what do you think? Of these 3, the one that has the symmetry is this one in the middle, and that's our bet for the pair right there. You see that symmetry in this aromatic ring system, and that's going to be a pair substituted. What about the other 2? Well, as we said, all those hydrogens are different, but think about what we just did with the OCH3. What does the OCH3 do? It donates electrons in, particularly at the carbons adjacent to it and across from it. Adjacent to it and across from it. And check it out. In the meta case, there's 3 hydrogens like that. And in the ortho case, there are only 2. And what have we got? 3 shielded hydrogens here, 2 shielded hydrogens here. Here's our meta, here's our other, and we're done. Isn't that cool? All right. So remember, protons in different chemical, electronic environments have different chemical shifts and can be referred to as shielded or upfield and deshielded or downfield relative to each other. While not everything about chemical shift can be predicted using simple arguments, much can. We can use many of the same inductive and resonance electron density arguments we have used in predicting and remembering the relative pKa of organic acids to also predict, or at least rationalize, relative NMR chemical shifts, because both phenomena are electronic effects. And you know, I can't say enough for just having some rough sense, so you don't have to look at tables all the time, of where these peaks are going to be on the spectrum. If you go from 0 to something like 12, you just cut this into regions 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And this region over here around 1 to 2, this is always alkane. This is just CH3s and CH2s that are not near any kind of functional groups. This region of 2, this is where we start seeing on hydrogens on carbons that are adjacent to carbonyl groups. This region of 3, usually right in here, sometimes a little further, is where we have OCH3, and it gets further and further down here, especially if it's an OCH3 or an OCH, if it's got a carbonyl group attached to it. We'll see later that the 5 to 6 range is where hydrogens on carbons with double bond to other carbons show up. And this region, 7 to 8, very important region, the aromatic, with the really shielded ones to the right of 7, the really de-shielded ones to the left of 8, giving us a clue as to what is on this aromatic ring. Way over here at 10, we have the H that's directly on a carbonyl group, the aldehydes. And way over here at 12, we have the HO C double bond O of a carboxylic acid. If you know this, you can go a long way and be able to solve these problems without looking at tables all over the time. Okay, well, I hope that helps, and I hope you've got it.